Not every factor that you can measure about something is going to correlate to a predictable or model or characterizable response, right? So we have to be able to figure out, initially we started in saying, well, we're gonna try to balance everybody and how they're playing by the rules, because we assume that all of the data points that we have something to do with the underlying process. It's usually a good idea at some level to analyze and see whether or not those things that we're trying to balance, the things that we're trying to create a multiple variable, multivariate regression for. You know, we have optimization, singular optimization, and then we have multiple variable optimization. And the multivariate optimization becomes much more complicated much more quickly. We end up in that space where we're having to determine, you know, which way we're rolling down the hill of the surface, of the high dimensionality gradient. All that stuff gets complicated, okay? And I know I'm talking about that in a very high level general sense. We'll revisit it at a later point, but let's just imagine for right now that we just sort of have a widget that kind of does that for us. Let's just imagine that we've simulated the concept of gravity inside the computer, and that whenever we put our assumption about the current consideration, the current configuration in multidimensional space that is the error surface, right? That when we let it go, it'll calculate the current consideration and then determine the direction of optimization and sort of roll down that hill. Okay, that's what we're going to let it do. We're going to start with an assumption, we're going to test it, we're going to make some adjustments, we're going to test that, and then we're going to see what the delta is between those two things. And then based upon that delta, it'll give us some indications as to whether or not we're going in the right direction and by how much. So here we say, if I've got multiple different directions to go down, and one of them seems to be useful, then we can optimize, right? And then it's something that is fixable. We can even utilize some of that characteristics of that descent toward the minimum as a mechanism to help weed out, you know, the from the goats when it comes to which of these elements is most useful. So the idea here says only a subset of predictors can be the case, right? So you can sometimes say, yes, all the predictors do well predicting Y, and then sometimes it's only a select subset. We're going to talk about that mechanism. We're only going to talk about it in a very cursory sense, and then we'll revisit it again in a little bit, right? So we're going to revisit it again later and talk about how those metrics actually decompose. And then we're going to say, how well does the model that we've generated fit to the actual data? That's the mechanism that we've started putting together with the R-square value. But we're going to look at some other mechanisms to be able to calculate that as well. And then we're going to say what responses or what response values should we be predicting relative to the data that's provided. Now, one of the things that I think is interesting about this is because thus far we've been thinking about the values that are in that column that we call Y as like a predefined target, right? You can only predict Y as the output. This isn't actually true in some cases, right? So in many data sets, you can think about it as an array. Everything is sort of has these tensors, these elements that link all of the items together, right? So you can select certain aspects and then they can be used to predict other aspects. So if you want to know what the temperature is, you know, or you know, you want to try to predict the temperature, you can utilize some weather data to predict some characteristics of the temperature data, you know, including stuff like it being overcast or cool weather coming in. But you can also predict rain, right? So if you predict rain, you're going to use your temperature prediction to predict the rain because it's going to have an effect on it. So which ones are the features and which ones are the targets is an arbitrary consideration. That's something we decide to do, right? So I say this is the target, this is the thing I would like to predict based upon these other factors and features over here. So this is when it gets complicated. This is the reason why these other questions matter, because sometimes you can have forward processes that are deterministic and relate to an output, but then the reverse process isn't necessarily true, meaning that that would then be a bad predictor for an alternative hypothesis, right? Predicting another state. Purchasing, likelihood of cross-purchasing, right? So the idea of saying, you buy a product, and each of you have like several similar products, right? I can predict your future spending perhaps based upon his future spending, right? but at the same time, I might not be able to successfully predict your future purchases based upon co-purchasing power, unless I had certain elements that came into play, right? So I can't always know all of those ideas based upon forward systems, because correlation does not necessarily imply causation, right? So correlation gives us the implication that there is potential causality, or at least potential characteristics that might play into it, but we may not have the whole picture. So by having either it's distributed over a bunch of different features, right? That's what we like to think about in truth. Because what's the point of using this for something that's really simple? Nothing, right? Really simple task, you can just figure it out on your own. Just think it through, run some basic math, do some averages, and you've got a rough prediction on it. But when you think about it, what is computational logic for? What is machine learning and statistical learning about? It's about taking a lot of examples and attempting to tease out all of the subtlety from highly complex interactive elements, and then be able to determine the interface from at a higher level than what we can naturally observe. All right. So one of the mechanisms by which we can adjust this system is something called an F statistic. And by the way, I wanted to follow up on P statistic characterization. I mentioned beforehand the computing of that was a little bit complicated. The truth is, if we make two assumptions, the reason why I said it's a little bit like not in our area, or it's not what we're going to really do here, because they actually produce it as a table. All right, so there's a correlation between T and P that is given as a table with the assumption of Gaussian distribution, right? So you assume Gaussian distribution, it flattens it. It's very much like how you can assume the chi of the distribution characteristic, or the distribution characteristics of certain types of continuous random variables in that way. Okay, so you get a table, and the table correlates two things together, and you get your P statistic out of that. So what we're going to do here is we're going to say that P statistic is relative to a likelihood estimation event. However, is this the P statistic inside of this equation? No, it's not, because it's italicized. Okay, remember we have two letters that are representing two elements of our data set. One of them is N, that is the number of samples in the data set, and the other one is P, that is the number of features in the feature vector, right? The predictors in that, of those features, right? So how many predictors do we have? So here it says TSS, so true sum squares, has what? That is related to the mean of y, so the distributional characteristic with relationship to mean of y, minus the residual standard error, residual sum squares is just the feature with respect to x, over the number of features, right? That's up top, that's the numerator. I'm saying I characterize the error with respect to the number of features that I'm starting with, right? So this is the relative characterization of the error with respect to that number of features. At the bottom, I do the same thing with the error, right? Residual sum squares over a normalization based upon N, the number of samples, minus P, number of features in the vector, minus 1. That allows us to be able to control for the initial interface state. This is based upon a polynomial expansion of the error estimate, right? So we say which of these works spatially. If the top takes into consideration RSS and true sum squares, then when I divide on the bottom with regard to N, the more samples there are over which the RSS is divided means that the value that's in the bottom here is going to end up getting, so RSS getting divided by a bigger number N is going to happen to what? What's going to happen to it? Let's think about something first. This one actually tells us a lot. It's going to tell us a lot. A lot is packed in here. let's think about what happens to residual sum of squares as the number of samples increases. What happens to RSS as the number of samples increases?
It also increases.
It also increases. Does it increase linearly with respect to n?
With respect to n?
So if, as n increases, so let's say as n goes infinity, what would happen to RSS? Would it be going to infinity at the same rate? This one's making you think. Okay? So we have 100 samples over which the error is distributed. We said that the error would decrease as the sample number increases typically, as a result of the fact that we're more likely to see more samples that are going to be aggregating toward the mean of the distribution, right? So as the mean of the distribution tends to aggregate toward that central limit, then we're also going to have a characterization that's going to be related to RSS over n, that n is actually going to get bigger slightly faster than RSS, right? So n is going to get bigger, and it's going to go, its increase in size is actually going to outpace the residual sum of squares.
Oh.
Eventually, right? Because how is RSS calculated? It's calculated based on the mean of x, the area, the range over which x is distributed. Yeah.
So it will what do you, forgot the word. It's like it will have a threshold RSS, like
kind of, not exactly a threshold. It will just stop growing as quickly.
So like it's like this.
Yes. It starts
Bare-
relatively quick and then it tends to linear. So it starts, it increases fairly quickly and then becomes quasi-linear, right? Or even sort of flat.
Flat.
Yeah. The relationship is saying that every time I add a new n, what is the likelihood that it's going to be contributing to the error in a way that is offset relative to the number of samples? Well, that converges at a certain point almost to nothing. Very little is going to be added to the residual as a result of adding a new sample on average. So this feature at the bottom starts to stay static. Also, TSS at the top, what happens to that? Since that has y and y bar, right? So it has the value of y and the mean of y. You notice that also is going to have a convergent expansion characteristic. So we'll also have p up there. Okay, so p remains static no matter how many n we have. We have 5n, and then we have 5p, right? That's going to be a problem. Why is that a problem?
That was 0.
We don't have enough samples to adequately understand the complexity of something that is five-dimensional with 5 values. This is the entropy consideration. This is the cursed dimensionality coming home to roost on us in a very clear way, that the F statistic is a mechanism by which we are going to analyze the quality of the distribution as the quality theoretically expands past a certain scale of necessity. So the F statistic starts to stabilize by the value in the denominator becoming pretty small, because RSS over n, right? It's a stable number by an increasing number that starts to get pretty small, but then the value up top stays pretty static after a certain point as well, right? So this starts to balance at a set point, right? It will start to balance. Enough samples relative to enough features will start to have a number that makes a certain sense, right? So a medium-sized number divided by a small number, you get a pretty big number, okay? So as the F statistic increases, what we're tending to see is something that is likely getting a better sort of correlate reward for increasing the number of samples relative to that number of features. So we said previously we wanted to ask the question, how many samples do I have to have relative to a certain number of features in order to get a certain quality of fit? The F statistic will kind of tell you that, right? So as you'll watch, as you keep adding samples, you watch the F statistic climb and climb and climb, and in the same way that both of these systems climb and then plateau, the F statistic tends to climb and plateau. right? So once you get enough samples relative to that number of features for this specific distribution, this specific sample set, right? You don't really need any more. You'll get some improvement, but you won't get as much improvement out of it, right? So there's a point of where you get maximum return from continuing to add n. Like I said, that one is a little bit complex, you know, as far as visually and what's happening there. There's a lot of moving parts, a lot of those interconnected gears like we talked about, where you have RSS on the top and RSS on the bottom, right? So both that measurement of error is in both the numerator and the denominator, and what we're looking for is the result of what is in the parentheses at the bottom, okay? So if n is 1,000, right, and p is 50, we have 1,000 samples with 50 feature vectors, or 50 feature elements within it. So we have 1,000 vectors of 50 elements. That's a pretty big array, not massive by any means, but pretty good size. But the consideration here is 1,000 samples capable of adequately representing the space of those 50 variables? And we can calculate it by plugging it in here. So we utilize, because TSS gives us the relationship of the relative variance within the target, we can have some understanding of how well that system fits. We don't really need to roll in the additional scores like the R-square in this space, because we're already considering it in a sense relative to what we said RSS beforehand was what? RSS over TSS was the R-square value. So now we have TSS minus RSS over P in the top, giving us an understanding of the relative fit with respect to that number of features. So as the number of features changes, as the number of features reduces, we have more significance is placed on those fewer features. Essentially, the number of features dilute the relative significance or relative value of the assumption. So if I assume that this event, this thing, is contributed to by all 50 of these various items, then I have to assume that there's some sort of equivalent contribution to all of them, right? They're all up behind the boulder pushing it forward. Is that likely? No. And in order to make that assumption, right, I have to say, well, I must try to provide everybody with some degree of contribution and significance. And so by the time you take the whole movement and then divide it out over everybody, it becomes such a small little contribution at each level that the process of trying to figure out how that boulder gets moved gets very obtuse, it gets very complex. It's hard for us to be able to figure out which one is which, what is making the significance here. So I said that high P, a large number of features that we're attempting to fit to, typically creates a problem with significance in those, right? So we lose significance by diluting it over a lot of features. So one of the methods that we use is a direct approach called the all subsets or best subsets regression. So I say some of these features I want to keep, I think are useful, and then others of them may not be the most useful. We call features that are not the most useful out of a set confusers. So if I hand you a bunch of data, right, and let's say my original experiment came from sociology or psychology research, where a lot of the information that was being worked with was self-reported. So what do you want to do in that space? If you're not sure exactly how all of these things integrate with each other and how they interrelate with one another, and you're developing an experimental design, how do you want to collect the data? Do you want to collect just the 5 things that you think are most important? Or do you want to collect 25 things, because keeping somebody there for another 5 minutes and getting those 25 additional elements gives you a little bit more wiggle room around the outside of stuff you think might be correlated with it? So what we end up with is a very wide net being cast out and then trolled back in with 5 features that actually matter and 20 features that probably don't make much of a difference, right? Now, what could be said there is, maybe those 20 features could, yes, in the future could elucidate some other issue, or could clarify what's going on with the other 5. But if I just said there are 5 features in these 25 that I think are the most highly correlated, how do you tell me which 5 out of the 25 are the ones that are the most important relative to that system? That's what we're going to look at here. We're going to talk about something called a subset, thinking about it from the perspective of like a set notation characteristic, that I have created a set of, this is all features, right? And then we're going to create some set S, which is a subset of A, right? So S being a subset of A, in this case. Now, how do I select this guy right here, the subset? Which elements of A are in S?
So if we compare if there is a relation with them.
Yeah. That's what we're looking for. So let's just do 5 and let's think about 3 of 5, right? So I have 1, 2, 3, 4, and 5. Let's say that I had 3 of these that mattered. How do I do that? I can select every other one, right? That's one set. I can just select the first 3, that's another. I can select the middle 3, that's another set. I can select the end 3, right? What ends up happening in this case?
3 is common.
Does order matter? I'm going back to my 394 with you guys. Does order matter here? No, it's the same set. So if order doesn't matter, then it becomes what? A combination, right? So it's just a combination relative to the scale of the number of elements within the set. So what we often do is we often analyze models from a perspective that allows us to examine all pair sets, or at least all pair sets relative to 1 minus the base of the pair set. So what we tend to say is that the capability of pair sets within best set notation is a factor of 2 to the p for the subset. So it is generalized here, within the way I've written this, it is 2 to the cardinality of S. Right? So if 2 is 2 features, then I have that number of subsets or regions that can be co-sampled out of that subset. So it says that if I have 2 to the p for a p of 40, what ends up happening there? Just pairwise selections out of 40 feature vectors ends up becoming billions of possible models that can be built out of 40 features. You have billions upon billions of models that we can now build because I am 2 to the 40th power combinations of those 2 features together, right? So building out, literally that is minus 1 feature the first time, and all subversions of that, minus second feature the second time, all versions of that. And then all sub-combinations thereof, right? So it's combining together all the possible outputs of the system. So it's multiplying each of those models in each of those states. Combination times multiplication times combination of that state. It is 2 to the 40th power for subsets. So we need an automated approach to be able to devise and then sort through all of that possibility, right? That's going to take a while. So reality, what we say here is we use 3 common approaches, and we're going to talk about these in a very basic sense, because I said beforehand we're going to come back and visit these, because we're going to talk about these again with regard to classification. But forward selection is a process by which we affix a problem, okay? So we're going to talk about best set at some point in time, so let's talk about this. So we're going to talk we say all subsets approach and best subsets approach. Best subset says that I enumerate all 2 to the p models, and I test all of them. So what happens in that case? I have to test all billion models. That literally is the only way I can know that I have made sure that the subset that I'm using is the best subset. Yes?
When you refer to features, could that be thought of as like the columns within the array, like crime rate or?
Correct. That's
Something,
exactly what
okay.
I'm talking about. So it's something, a feature is something that I can measure
Right,
relative to a region that I can enclose within a population.
okay,
So I have a city, right? I create a district, and now I can measure something about that district. Crime rate would be an example. Population density would be an example. Access to public transportation is an example, right? Ethnicities of the various individuals inside of it. I have a student who's
These are-
doing a search grant based upon demographics, so that's a prime example there. Yeah.
So these are the features like crime, populations, and the age and.
Correct, right?
Okay.
So they're quantifiable elements. And what am I attempting to predict?
Mm,
Whatever the heck I feel like it. Okay? Really, that's the truth
so
of it,
that's
right?
the arbitrary part of it?
My student that I'm working with was in my 394 last year. He's working with search. He's wanting to understand the expansion of Latino populations, Kansas City metro, right? What is going to happen as a result of this? So he's thinking about it with respect to the idea of access to education, healthcare, services, housing, those kind of elements, right? How do we do that? We say, well, there's a likelihood that the current population density of a region will likely continue to expand at the same rate that it has been expanding at. So we need to know how many people were there over a certain period of time. We need to know what access they did have. That's a feature, right? We have how many were there, what access they did have, what kind of educational access they had, crime prevention statistics, all those characteristics, housing, cost, and analysis. And then we can do what? We can say what we had before, what was like. That's our model, that's our a priori, that's our training set, right? And then we are going to make some assumptions. We're going to say what's likely to happen in the future. This linearizes the model. So then I extrapolate based upon my previous understanding from those features, and I attempt to tell you what the population density is going to be. That's why. My target is population density, or total population within the system, right? Either one of those are accessible as a value, as a metric from what we're talking about beforehand. The idea is I can collect whatever features I think are going to be related to the target. And now what I want to do is I'm going to collect far more features than I actually am sure are related to the target, including things that might seem ancillary or additional outside the scope of our interest, so that we can tie in those elements to our desired track, our desired target within the space. Do not feel ashamed for asking that question. Is the fact that I love the fact that it's been asked, because I think so many students sit in here and go, it's just a word I need to memorize. No, it's a concept that's encapsulated in there. When I say feature, okay? I've talked about it before and I'll throw it out here again. It's like playing that little game, Guess Who, right? So if I wanted to try to eliminate people from this room, what do I have? I've got some options in here, all right? This is my Guess Who board. It's always my Guess Who board. I'm just gonna flip down, you guys,
Start
right?
with classes.
I could start with glasses, right? That would do a thing, right? I could start with guys with follicle disadvantage in the superior region. Trying to be very political about this, all right? So I can start with people wearing hats, all right? I've got four hat guys, okay? So I've got four hat guys. What that gives me the ability to do is I can flip your tiles down. I don't have to worry about it if they say no. But what if they say yes, it is wearing a hat? I go, awesome, that is a super discriminant feature, right? Everybody else gets flipped down and I've only got four hat guys left, right?
When I play that with my daughter, that's how I teach her how to play the game. Go for the most defining feature possible.
So how do you determine that?
Well, when
Could we do
it
that?
presented
Can
on
we
the
take
board.
Guess Who? Can we take Guess Who? And could we segment it based upon frequency characteristics? How many of a certain individual relative to a certain feature within that set? Yes, the board was built with that.
Right.
The board was built as a discrete set of probability likelihoods to make it incredibly hard to initially ask questions that remove anything over half of the board population. Right? The spread, the variance over which those features occur is that a feature may only occur usually within a quarter or less of the population that is prescribed to you. So from that perspective, it becomes very hard to figure out which feature becomes the most powerful in your predictor outcome. Your predictor is to try to find the singular target. So now what have we done? We've done the definition of trying to figure out that you have a subset that contains an individual. Now the individual is going to be prescribed by the remainder of removal, right? We remove every other option except for the individual we're interested in. Okay, so what I'm describing here when I talk about features, I'm the idea of things that I can measure in order to attempt something else in order to predict something else that I've measured, right? And I can flip around who is Y and who is X, but I'm always going to have one Y, I'm going to always have one target. Now what happens within clustering is I don't use any of the element, I don't use any feature of the system, label or not, in order to figure out which group they're in. So from an unsupervised perspective, I'm just looking to see whether or not hat guys tend to sit together, right? Or whether or not people that are follically disadvantaged might sit together, okay? You're not even really follically disadvantaged. You can just grow your hair. You just choose to make it shave.
Yes.
So the idea being that we have people that are shaving their heads and people that aren't. Are they sitting in clusters, right? Can they be grouped in a way that made sense? And would that give us new information about the likelihoods of them sharing additional features in other spaces, right? So their correlations create adjacency in the feature space to create little clouds in which the things tend to aggregate together, right? We notice like tends to be around like, so we can utilize that characteristic. Now, we will use unsupervised methods for the process of feature selection later on, right? We can select features by understanding of non-coupled elements. We can also create new features based upon the combinations of existing feature sets. But that's beyond what we're talking about at the moment. Let's talk about the idea of forward selection. So I have my 5 features here. So let's start on this again. I've collected 5 metrics. Right? We could do this for weather. We'd say temperature, relative humidity, right? Wind speed, wind direction, and let's say historical data with regard to the previous temperature on a previous day, right? So let's say forward feature selection says that relative to some target Y, right over here, right? So Y in this case is degrees, so we want to make this guy happy. So it says, well, what if I just say that the only feature that really matters is what the temperature was last year? Okay? That means my model will now contain one feature. And I will attempt to predict Y utilizing that one feature. I take the 5 that are possible and I just try to do it with just one. Okay? I repeat the process for all possible just one configurations, right? And I try to see which of those just one configurations is the best. I can also use something called an information criterion, in which I can try to determine the power that that specific feature has relative to the other features. We know one feature is more likely to have a stronger possible outcome as a result of correlates. So I could run a correlation coefficient on the feature, and I could sort to determine which one I'm going to use first as a metric. Now, I say, okay, I did one, and one, it kind of worked okay, right? But I didn't love it. So let me go ahead and just group in another adjacent value. Now my feature set consists of 2 elements. So I'm going to have beta naught, beta 1x1, beta 2x2, right? And that's going to be features 4 and 5 from our original data set. Now, I continue on this process, assessing an improvement, right? So between the model, so let's say the hat, F hat, for the, we'll just say at feature 5 was the only element within the set, right? I'm going to get some error that's going to be a result of this. So error as a result of this estimate. And then I'm going to get another error here as a result of additional estimate. This is just me making some quasi-mathematical notation to go along with what we're talking about here. This holds up, but isn't necessarily internally consistent with all of our metrics. Okay, so I have one that contains just 5, right? The error that just contains just 5. And then I have one that contains the error for 5 and 4, right? This is forward selection, meaning I'm moving forward through the data set. I'm continuing to add a new element every time I create a new model. Now, how do I determine whether or not, what do I want to have happen here? I want to have 5.4 be better than 4, or than just 5, right? I definitely want to have 4, or I'd say better, so let's say error. I actually said error, sorry. I want to have error be less than, all right? Sorry, I did this backwards. Don't let my bad math confuse you. Okay? I was originally thinking about which model was better, right? But now I actually know I put error in front of it. So how is that better? Oh, it's less error, all right? So flip around here. Less error. So error went down by selecting the additional feature. Meaning that the additional feature that I added more information to the system such that I was able to, by combining, our powers combined, Captain Planet, we're able to create something new that makes the whole thing better, right? It does better than any individual character. So we have one originally, and then we're going to keep adding new elements to the system, right? So we'll have another one over here that will be hopefully 5, 4. Let's say that the next one we added was 2, right? Because 2 became the next one that was of interest. Why would I say 2 would be the next one of interest? Let's say that I ran 5, 4, 3, right? I ran 5, 4, and 3. Whoops.
But the error.
And what happened?
Error increased.
Yeah, this is error over here. Error actually went up. Right? Error increased. So I said, nope, no. So what do we say about that feature? We say relative to that set, that feature is a confuser. It provides some information, but the information it provides tends to lead the model away from the true underlying relationship, right? Now, what's one of the problems with this is that there could be some subset that we never explored. Let's imagine that because we sort of eliminated 3 from this possible search option, let's imagine that 5, 3, 2 was actually like much less. Splitting off of this branch, right? So if I combine together the information in 3 and the information in 2, 2 sort of mitigated the confusing factor of 3. Something about how they integrated together, the whole outweighed the sum of its parts. This is very possible and actually is incredibly likely with regard to features. Certain features will, in combinations with one another, tend to create additional valuation with respect to the systems. So we say that we fit linear regressions, we fit p-linear regressions, and then we characterize them with respect to the null value. So we're going to end up here with the possibility of being able to compute a t-statistic and get p from the table, right? And so we can say whether or not there's a statistical significance. So once we calculate significance, we rank these in terms of significance, and then we attempt to add first to the 2-variable model, right? Afterwards, by adding the next likely value and computing it relative to the residual sum, right? So the residual then will be calculated from the output. We continue forward until we satisfy a rule, right? What is one of the principal rules with regard to this? It says I must have at least one feature, okay, in order for it to be a valid model, otherwise I'm just null hypothesis, right? What's the null hypothesis? I don't need any features, I just take the mean of y. The initial hypothesis is I feature 5. Second hypothesis, feature 5 and 4. Third hypothesis, 5, 4, 2, right? Whichever one is superior, so from a model selection standpoint, whichever one produces the lowest residual is going to be the model that I tend to select. I keep doing this until I either hit a value that is enough accuracy, right, a low enough error, to be below my threshold. Now, why would I want to do it from that perspective? We have 40 features initially, and we're trying to sort out, let's say, or 25 features, that's what we said originally. 25 features, and we wanted to select 5. So let's say that our goal is to only get to 5 features. So we try to run through this system for forward selection until we get the 5 best features that we're able to get out of the set in this fashion, right? Only adding the next one that seems like it would give us the next best assessment based upon the correlation. Or we say we would like to get below a certain amount of error. That allows us to be able to continue adding features until the model has reduced to an absolute minimum. We always want to have, as part of the target for feature reduction or subset selection, is the idea is we want to take something, we want to have fewer features than we started with, right? If you go back and you keep adding, and you add all of them back, then you're back where you started with. You didn't get anywhere, okay? Question? Okay. So if you add all of them back, you're done. You wasted your time, okay? The opposite, well, I already went to this. All right, so forward selection is how you do it forward. Backward selection is how you do it backwards, okay? So you start with all of them and then you take them away. These are super, like, if you understand how one works, you understand how the other one works, right? So this is essentially the, I guess you could say this is the null hypothesis of the system. The reason why I say this is the null hypothesis of the system is it's not truly a null hypothesis. It's saying I'm starting assuming that everything, it's the inverse of the null hypothesis, literally everything matters, okay? First case is everything matters, and I'm never going to be able to get any better than that. The second one is I can remove feature 1, right? Why I'm working for the bottom, I have no idea. It's just arbitrary. It's just a direction. I picked one. Now I have created a subset that contains one less item. I continue to do so for all compartments of the system, right? And iterate through that same process. Now I have 1, I left 2 out, right? What's going to happen now? I'm going to leave 3 out. I'm going to have 1 and 2. The 3 left out. So I can iterate through the process of all of the subset configurations. Now is this the same as the best set selection? No. Because by iterating through the process here and selecting only one item to remove per systematic epoch, I'm not creating the same level of complexity. There's also this idea of consideration for the early stopping. So we say that p minus 1 is the first iteration, then p minus 2, then p minus 3, and so forth. So subtracting one feature every time I move on. So if I start off, I've got 2 options. I can do breadth first, meaning I can look at every combination of minus 1 feature, or I can do a depth first approach in which I continue to remove the weakest feature from the RSS multiple times until I get to a subset state, and then go back and restart from various other positions, okay? So this is a sort of tree, state-based tree search process by which we eliminate features. We either add them and increase the complexity of the model until we find a satisfaction to our constraint, or we start from all feature characteristics and then subtract 1 at each relative layer until we end up decreasing complexity.
You answered the question that I was going to ask,
Oh,
but
okay.
I decided to let you go a little further
Sometimes
because I was going to ask if we could just iterate through
Yes.
all the combinations of the subsets
Yeah.
to find out which would be the best.
So one is the one, okay, if you guys want to just think about these in terms of like standard tree search methodologies, this could be re-described as best set is brute force, right? It is complete and optimal with regard to algorithmic constraint design. However, forward feature selection and backwards feature selection are neither complete nor optimal, right? But they're locally optimal. Meaning, what are these? These are greedy approaches. They take only the best option at the localized state and determine how to move forward. So which item is being left out or dropped out is upon the local gradient or the local error estimate. I don't consider what could happen in the future based upon if I drop 2 at this level and then drop 5 later, right? Now I end up with a better set. But because of the fact that 5 tended to be the quality, seeming quality predictor at the highest state at its independent level, then I keep keeping 5. I'm never going to remove it. But sometimes a subset without 5 may actually be the better subset. But we will never explore it because it doesn't seem viable. So the only way we'll actually ever get here is by the exploration of all possible branches of the tree. This is an issue of time. Since the time complexity characteristic ends up being billions of possible model configurations we have to run. We need to get a solution now. So an 80% solution today is far better than a 100% solution or 98% solution 3 years from now, okay? So while we can potentially attempt to implement an ideal subset configuration or best set selection for some models, it's a diminishing return on the amount of time that we spend relative to the amount of accuracy that we gain by searching through all possible subset configurations. So forward feature selection and backwards feature selection are the two most sort of common methodologies by which we use sort of a greedy approach to RSS minimization by iterative selection and moving forward through possible subconfigurations, either adding one in forward selection, adding one each time, the next best candidate, or backward selection is you are the weakest link, goodbye, right? So whichever one is the worst out of the set, or whichever one was not performing as its own independent RSS based upon the metrics, the informational characteristics method, we call this information gain. So in information or data science theory, the notion is that the relative information gain of this feature is so small that it is negligible. How much we know about the system now relative to its inclusion is not enough to merit its inclusion relative to the curse of dimensionality, right? If I eliminate a feature, what did I do? I reduced the area of the search space by an entire dimension. What happens when we do this with regard to 3D down to 2D? We love it, it's beautiful. It's a massive compression of the amount of area that we have to search and optimize in. So by reducing the dimensionality of the system, we end up with far easier to model relationships between the elements, and it gives us the option to be able to search through much more quickly and come to a viable potential conclusion. Okay, we'll continue on with this and talk about more to come with chapter 2 still, but we'll lead into chapter 3 probably next time.